So hello everyone, my name is Charles Bonnineau. I'm a PhD student at Beacon, TDF and INSA IETR of Rennes, and I will present you my research work on multitask learning for VVC quality enhancement and SuperResolution. So this research work was selected as an oral presentation for the PCS 2021 conference and was done with the support of Wassim Amidouche, Jean-François Trabert, Nati Sidati, and Olivier Desforges. So let's start with a little bit of context. So VVC stands for Versatile Video Coding, is the next generation video coding standard, which was released in July 2020. So this new video coding standard offers around 40% of bitrate reduction over its predecessor HEVC. So the application is for the bitrate reduction of highly immersive video formats like 8K, HDR, or HFR for improving the quality of experience of the end users. So in parallel, many learning-based post-processing modules have been investigated for video coding to improve the efficiency of the existing standards, like, for example, SuperResolution, which can be used in a coding pipeline to recover high-resolution details from low-resolution compressed inputs. So some previous works have demonstrated that the use of SuperResolution in an adaptive resolution scheme can save bitrate at low bitrate compared to full-resolution coding. And moreover, it allows a sort of spatial scalability to be done because different resolutions are available at the decoder side. On the other hand, it's possible to consider quality enhancement without upscaling, just to remove the compression artifacts that are introduced during video coding. This kind of approach can be used as a pure post-processing module or integrated in the coding loop as in loop filter. So all these learning-based approaches are mainly based on convolutional neural networks that are known to require many parameters to be stored and transmitted to be efficient. So it can be a problem. Let's give a quick example. Here we have an input image ILR, for example, which we want to compress using VVC with a coding and decoding steps using a given quantization parameter. Here we selected QP22 for the example. The quantization parameter is used during compression to define the level of degradation introduced in the reconstructed image at the price of a lower bitrate. So it gives us an indicator about the level of degradation. As discussed before, we may want to perform some post-processing using CNNs, like for example here, we want to do SuperResolution using a first dedicated SuperResolution convolutional neural networks. Or we may want to remove the compression artifacts by using a quality enhancement network, here optimized for QP22. Or we may want to use another network optimized for another level of degradations, and so on. Here we see that we accumulate a lot of neural networks, and there is clearly a waste of parameters. Indeed, in practice, all these neural networks are trained and deployed independently, which result in exploding the number of parameters, which is impractical for devices with limited computing resources like TV chipsets or smartphones. But hopefully, it exists a way to benefit from the redundancy between the different models to reduce the total number of parameters while maintaining a good quality of reconstruction. This is what we proposed through multitask learning. So multitask learning has been first proposed for high-level vision tasks, like, for example, segmentation, image detection, or depth estimations. But here we are interested in using it for low-level vision tasks, like SuperResolution and quality enhancement. So here we have at the right of the slide the schematics of our approach. We take as input the degraded reconstructed image with the associated QTP map that gives information about the level of degradation. This input is sent to the shared network that is splitted at the end toward two different task-specific submodules. So here we clearly see that we reduced the number of parameters while maintaining, while allowing both tasks to be performed and making the networks able to generalize about around over different level of degradations. Let's have a look on the architecture details. So for our architecture, we selected the EDSR network, which is the state-of-the-art for super resolution. So we just adjust the networks to make a parameter sharing architecture. So here, as we've seen before, the input image is given as input to the network with the QTP map by a concatenation about the feature around over the feature axis. After this input is done, is passing through the shared network and is splitted at the end of the network towards the different submodules. Here, the QTP map corresponds to a uniform map with the current QP under the max QP value, which is 63 in VVC. For the training details, to train a multitask network, we need a multitask loss function that is defined from the two task-specific loss functions. Here, the loss function for super resolution and the loss function for quality enhancement. In our work, we compute this both loss using the L1 loss metric and add them in a weighted sum to get the multitask loss. For the training parameters, we selected a learning rate of 10⁻⁴, a batch size of 8, and the optimizer Adam. To initialize our networks, we first, as the architecture is mainly based on EDSR, that is the state-of-the-art for super resolution, we first train the network for the super resolution tasks on raw images. Then the pre-train rate are used to train the overall network by using the multitask loss. For the datasets, we use Dive2K as a training set, which is a well-known image database, which consists of thousands of different high-resolution images with different special characteristics. Here in this work, we use 96 by 96 patches for the training, and we validate the performance on the set5 image dataset, which is an image dataset consisting of 5 images. And in our work, we also test the performance on the GVET CTC video sequences encoded in all-intra mode, because in this work, we are focusing on all-intra. So to generate the dataset for training, we first downscale the high-resolution images using a bicubic filter and encode it with VVC in all-intra configuration using the QP parameters 22, 27, 32, and 37. So let's have a look on the performance. Here we have first an ablation study, which is dedicated to highlight the different components of our networks. So first, we are interested in evaluating the performance of training one network for all QPs versus training one model per QP. We are also interested in evaluating the impact on the QTP map on the performance. And we are also interested in evaluating the fine-tuning against the from scratch training. So here we evaluate the performance by comparing the reconstructed image with the ground truth using the PSNR and the SSIM. And the delta PSNR and the delta SSIM stands for the difference between the reconstructed image with the multitask networks on a bicubic filter for the super resolution, and the difference between the input image and the enhanced image for quality enhancement. What we can observe is here. In the table, we have the different configurations for the different tasks and for different QPs. In the left, we see our model, which is trained for multi-QPs with a QTP map and with fine-tuning. And the first interesting observation is that fine-tuning improve both tasks, improve both super resolution and quality enhancement tasks. However, although the fine-tuning is done on, the pre-training is done on super resolution. Another observation is the difference between training one model for all the QP and training one model per QP. We can clearly see that the QP map helps us to reach the performance of dedicated training per QP with multi-QP networks. So it allows us to reduce the number of parameters by 4 because we have only one model for the different QPs. That's it for the first study experiment. Now we want in the Ablation Study to evaluate the interests of performing multitask learning against single task learning. Here in the table, we have the different methods with different baselines. So here, baselines B stands for the number of residual blocks used in the neural network. So the more you have a residual block, the more the parameter you have, and better performance you have. So here we compare single task for super resolution, single task for quality enhancement, sequential performing of first quality enhancement and then super resolution, and finally the performance of the multitask network. Here the observations are interesting. We can see that the sequential configuration does not perform significantly better than a single task approach. And for the same number of parameters, if we look at Q04, SR4, and for single task super resolution SR8, we have the same number of parameters, but sequential configuration does not perform better. Another observation is that if we look at the multitask learning, we see that for the same number of parameters, if we look at super resolution, for example, we maintain the quality of reconstruction by halving the number of parameters. It can be explained by the fact that actually both tasks of quality enhancement of super resolution learns very similar features. And we can go to deeper model to learn better representation. I propose you to look at a small visualization here to illustrate the fact that both super resolution and quality enhancement tasks are correlated. We can look at inside different task-specific networks. So here we have a quality enhancement network dedicated only to quality enhancement, and a super resolution network dedicated to super resolution only. If we extract the learned filters, so that filters are what the networks learn. So if we sort it by the less similar to the more similar to the less similar, we can see that actually super resolution and quality enhancement learns very similar patterns, very similar filters that are computed twice if we consider separate networks. If we go deeper on the network, we can clearly see that we have also very similar features. So for the model evaluation, we also evaluated the model, the multitask model against the single task models. For super resolution on average on the GVET CTC sequences, our multitask network, for the same number of parameters here, we save around 3% of PSN of bitrate for we save about 3% of bitrate for the same PSNR, and for quality enhancement we are more about 2.3% of bitrate saving for the same PSNR. So what we can conclude of this study and our model. So as the literature says, CNN-based post-processing models outperform the state-of-the-art on a lot of low-level vision tasks, like for example the interpolation filters of Langsos and bicubic. But those learning approach requires a lot of parameters to be efficient. That is a limit for some devices. In this work, we set up a training strategy based on fine-tuning and prior information that allow us to generalize over different level of degradation with a single neural networks. And we also set up a multitask learning approach, which exploits the feature redundancy between the tasks. As we have seen in the visualization, all the super resolution and quality enhancement shares a lot of features, so we can compute it once and use it for both tasks. We show that we get performance similar to the state of the art for both tasks with actually an additional task. So in future works, we plan to integrate the temporal aspect in our scheme, because those learning approaches suffer from temporal consistency artifacts when applied on video. And moreover, we are interested in using it, integrated it in a scalable codec. So that's it, and thank you for your attention, and I'll be pleased to answer your questions.
Thank you very much. So now is the time for questions, and I can start with one. Can you go back to slide 12, please? This is where you regret having so many animations.
A little bit easy, and I guess it will not stop.
Normally, you can type if you just type the 12 number on your keyboard, you can reach the slide directly.
Okay.
If it's PowerPoint, at least. Yes, this one. How was the multitask loss selected? Was it an empirical value that you selected, or is it somehow the best value found in the literature? How do you find this value?
You mean L1 loss? Or
no, the alpha.
The alpha, okay. The alpha, actually there exists a lot of mean to perform multitask loss. Here it's just an average sum, a weighted sum, sorry, and the alpha was selected around over different values using a grid search on different values from 0 to 1. So it's empirical, but it exists a lot of approach to merge these two losses. For example, one interesting literature approach is to use the uncertainty between the tasks to put more interest in the loss that are the less uncertain, or you can dynamically weight the loss regarding the previous iteration if a loss is very unstable. Maybe we have to consider weight it more, but that's very fancy approach that are very efficient for high-level vision tasks. For example, when you have to do multitask with I don't know, segmentation and depth estimations, those approaches are very efficient, but we tested it in our case, and for low-level vision tasks, it seems that weighted sum is the best way to do it. So
okay, thank you.
I think I can continue.
Yes,
can you go back to slide 11, please? I'm not sure I understand the QP map. Is it just a map with the QP value added to the other features? Because I think there is only one QP value for a given quality decision.
Yes. It's just a uniform map. So it's well known from the literature to do this. It's just a uniform map that considers the actual copy used to compress the frame normalized, and you just give this map as input to the network, and it works actually as an attention map that gives informations to the network that, for example, the image is degraded a lot or not.
Okay,
I don't
so
know if
it is just to simplify that you use a map and not just a simple value.
Yeah,
okay.
Exactly, yes. But it could be done by conditional code, by conditional thing. But here we just it's a hack actually to give the value to the network.
Okay, thank you.
While you're on this slide, I have a question also. So you selected the EDSR network as the baseline network for your multitask work. Was it because it was okay? I guess it was the best one for the super resolution problem, but why did you select the super resolution network instead of the quality enhancement network? Is it because this network is bigger than the quality enhancement, or is there another reason?
Actually, the quality enhancement single task approach I set up in this presentation and in this work is based on EDSR. So EDSR is used for all the tasks in single task network. I'm aware that EDSR without the upscaling is not the best way to do quality enhancement, but in this work we simplify to simplify it to simplify the study actually.
Okay, thank you.
I have one question. Just to clarify that this QP map also we use it because in a real case, in a real coding, we can have different QP by block. Just in this case, we have just one, but in like adaptive streaming, we can have different QP by frame and different QP by block. That will give us not uniform map. Like it makes the solution more adaptive to real cases. And they have another questions about if you can tell us what are like the limitations of this solution that is based on super resolution only.
Yeah. We at the beginning we were just interested in improving super resolution actually, but by doing multitask learning, we demonstrated that we can add another task while maintaining the quality. But here's the quality enhancement. I think underperforms with these networks against the state of the art.
My question, it was like, what is the limitation of using super resolution? Like, not in multitask or single task, like for different contents, like
yes. Okay, so I said that super resolution can be used to recover high resolution details from low resolution compressed videos, but actually it have to be done most of the time dynamically, because super resolution is very sensitive to the nature of the content. So in some case, when you apply super resolution in a coding pipeline, the performance can be terrible if we have a lot of details that cannot be recovered using this kind of network. Full resolution coding will certainly works better. So in most of the cases, super resolution is used in an adaptative way. So it's also future works that have to be considered to show the performance of super resolution in an adaptive of multitask in an adaptative schemes. But here, super resolution cannot be just used as a magical tool to any contents.
Thank you.
What is the use case for this kind of approach? Where is it supposed to be deployed? In the head-end, in the receiver, in the network, and or implementable DCs in terms of practical platforms?
In this work, we are just interested in post-processing, so it would be deployed in the receiver, but it can be imagined that we want to, for example, update the weight through the networks. It can be one use case. So, but the main use case is to perform the upscaling in the receiver. Yes.
So receiver are capable of doing that real time and.
No, not really. Actually, ESR is one of the most is very complex. For example, in a very powerful GPU, we can be around 1 FPS, 1 or 2 FPS for an HD video. But we can consider lightweight networks that can integrate this multitask approach. And but for the study, we selected the state-of-the-art that is not really realistic in terms of implementation in real-world use cases.
Okay.
One of our objectives in OpenVVC is to use real-time decoding with this quality enhancement and super resolution in like device with the GPU in real time. Like we can have decoding, and then in optional we can have quality enhancement or super resolution, but using just one network in real time. It's a challenge actually we want to do.
I have
to be deployed
question.
in
yes. So this work has been done on intra frames, right? If I understood correctly.
You ask if it's only for all intra?
Yes.
Yes. For the experiment, we just consider all intra configurations.
So if you want, one day you want to do it for inter, because in inter the challenges are different and the characteristic of the signal. I mean, you need to consider other stuff than the texture. Do you find it, before doing it, I don't know if you have already started doing it or not, but do you think it will be easier because you have more information from temporal information in addition to spatial information, or it will be more challenging because it's inter, and inter is always more complicated? So what do you think is the most challenging thing if you want to do it in inter, and what is the possible advantage of doing it for inter?
Yeah, actually, the main challenge is to keep the temporal consistency. So that when you do it on video, we clearly see that there are artifacts in temporal. But in the other end, using temporal information in SuperResolution can actually help the SuperResolution as you are considering the neighboring frames, which contains a lot of information about the current frames that are sampled during sampling or downsampling. And by using those neighboring frames, you can get back this information and use it to recover the missing details. So it's challenging. Actually, using temporal helps to have better performance, but the challenge is that it has to consider highly complex motion compensations blocks or optical flow blocks. So it's not in the. It's hard to consider, as this kind of approach is hard to consider in real time. Adding temporal blocks could make it worse, actually. But I think if we get this information in temporal information, we can improve the performance at a price of complexity.
I mean, since you're doing it as a post-processing module, you can always compare whatever temporal information gives. You can compare it with taking the same strategy and applying the same process to all frames, no matter they are inter or intra, and then you can compare it to that to see if the additional complexity is worth it or not.
Yeah,
right? That's a potential, basically.
Yes, exactly.
Thank you.
Thanks.
But at least maybe we need to retrain networks for enter, because like distortion we may have in intra and inter may be different. So applying applying this network on enter.
Yeah, sure. Same strategy with a dedicated network, probably.
Yeah, at least, yeah.
Yeah.
Because then the second option is to provide to the network several frames. And this will also have some propagation in terms of quality enhancement.
What is the impact of the codec used prior to this processing? Is it trained to handle all kind of encoded video? Or?
So in this work, we just focused on VVC, but obviously it can be applied to any codecs. It's one of the advantage of this approach. You can just apply it on any codecs if you have the right training data sets. But for this approach, we didn't go deeper on it, and we just selected the VVC. But actually, it would be an interesting test to compare, for example, against the gain with VVC, against the gain we can have with AV1 or with EVC, but we didn't do it, actually.
Yeah, and the one challenge here is because these networks are very sensitive to the training. And if we change, for example, the codec or change the type of distortion, the performance may draw back. So it's really challenging to provide some solution which generalize well to different codecs. And this is really challenging because even in challenges that was organized in CVPR or in different contexts, we focus only on one codec and one type of distortion. But I think here we really need generalization to target several codecs and
so
type of distortion.
Here I see a QP map. It means that it's the codec, the underlying codec is using some rate control.
Here we just encode it with in this experiment just random access with VTM, and we just get the QP map associated to each frame. But
so it's not really a QP map; it's just a QP per frame.
Yeah, exactly. It's just the QP of the frame represented in a uniform map that is normalized.
If dynamic QP adaptation is used inside the frame, how would that impact the method?
Actually, if we have different QP per block, for example, in the frame, I think it would help actually the network, because granularity of the degradation is better. Here we just have one value for all the frame, but if we have a value associated to different areas, it should help the networks. So there are very interesting works that perform this, that use, for example, Fateme had become not use the QP map with block per QP, but use the prediction instead of QP maps that gives better performance. But yeah, QP map is just the less we can have from the QP.
Yeah, we can see it as a way for the generalization of the network for different bit rates or distortions. And we can suppose that this map will help if we are in the context of adaptive bitrate or adaptive QP by frame, that the network will generalize well to this solution, and we can target several bit rates in real time with only one network.
Well, I think we don't have any other question, do we?
I do. I have questions, but I can keep some of them for the conference. Well, just one question. So you are presenting your gains as BD rate values, just one number for sequence, but do you remember if you have if your method has a preference over a range of bit rates? Is it performing better for higher bit rates or lower bit rates or mid-range, or it's a uniform, the performance?
For super resolution, it's clear that the more details you have in the low resolution image, the most the super resolution perform well. Because, for example, as I remembered, for example, for 8K sequences, if we take low bit rate, for example, using QP37 in random access, the difference between performing super resolution and a log-source filter is around 0.5 dB in PSNR. But if we go to higher QPs, it can reach, for example, plus 2 dB in PSNR. So it clearly depends on the quality of the resolution inputs. So the most you have quality in the inputs, the most the super resolution perform. The better the super resolution perform.
Okay, thank you.
Did you conduct some subjective viewing, subjective testing?
It's planned, but when we do expert subjective tests, super resolution is very smooth. But we didn't compare it for the moment using subjective tests with subjective tests. But as viewer and with expert tests, super resolution is performed very better than long source, for example.
One thing that is always interesting, personally for myself, is that when we do this kind of CNN-based post-processing, no matter it can be super resolution or filtering, sometimes I ask myself, as humans, we compare PSNR and say that there's an improvement. But as a human, I always ask myself, maybe CNN is making some artificial content that are not sensible for us. For example, I have seen it that some post-processing algorithms change the face, and they may look good PSNR wise, but for us as human, they look weird. So yeah, I'm very curious to know, just in general, not about your work, but CNN-based post-processing methods, how do they perform? If there's a subjective test if there's a paper that has already done that, and you know about it, that would be great to share.
Yeah, actually, there are different strategy for training. We use, as I said, we use L1 loss to minimize the loss, to train the network. So the L1 loss is quite related to the PSNR. So when we minimize the L1 loss, it has an impact on the PSNR. So the PSNR is not as out for evaluating this kind of reconstruction, but they are super resolution based on GANs or perceptual loss functions that consider more the semantics of what they are inside the contents. Here, the super resolution or filtering will hallucinate new details that are not that may be not in the source image. So, for example, in broadcast, as you said, for faces, it can be very annoying because we don't have in using that kind of approach, we don't have all the control of what is reconstructed. But by using pixel-wise loss functions, it would be okay because it's mainly related to the PSNR. So.
Yeah, and actually people that were working from machine learning, they usually are excited by presenting results with GANs, for example, that is based on generative models. But I think this is this approach can generate new distortion or new colors, which are not accepted in coding, video coding on image coding community. But it's yeah, it just I think from which community you are, something you are happy because you're having a very low bitrate performance, but you can generate some distortion which are not accepted in compression community because we want some fidelity on the pixels, which is very important for industrial broadcaster, etc. At least maybe it can be interesting in the context where we target very, very, very low bitrate, but this use case is not very popular, I think.
Okay. Do we still have any questions? Okay. Well, thank you, Charles, again for your very nice presentation, and good luck, I guess, for the same presentation in PCS.
Thank you, everyone.
Thank you. Goodbye.
Bye.
Bye-bye.